We'll see if more people show up, but let's start and let's see how far we get. I don't know if we'll get through everything today. But anything we leave for Thursday will be pretty quick and not super hard. I think today, well, you'll see. But yesterday we had this stuff, which was basically using geometric series to represent these rational functions, 1 plus x, or 1 over 1 plus x over 2 minus x. And basically the idea is just to take these geometric series that we know add up to what I'm circling right here. Wait, did I share my screen? I did. Okay. We know they add up to what I circled right there. And so we can basically insert or edit the geometric series to get whatever function, whatever rational function we want. So here are some examples. Here we wanted 1 over 1 plus x. And so we changed the r value to a negative x. That way we got 1 over 1 minus negative x. And that makes the 1 plus x. And same idea here, same idea here. And now we're at this problem. Find a power series representation for the function determinants radius of convergence. Oh, by the way, I've been meaning to say that for all these problems, like in this first one, these were little leftover notes that I forgot to erase from last year. What I was saying with this that I highlighted in orange or underlined in orange from last year is that you could always try to do this the way we've been doing it, which is like find the function value at 0, find the derivative at 0, find the second derivative at 0 times x over 1 factorial times x squared over 2 factorial. Remember this from a few days ago? And you would get the same answer, or you would get an equivalent answer. Like that's always an option. It's just I saved myself time because I was like, oh, I know if I did this, I would get this as the answer anyway. Or some equivalent function as that. But plus, one, I wanted to save time. Two, I saw that if I wanted to do this, I would need either a chain rule or a quotient rule, which would take forever. And doing that 1, 2, 3, 4, 5 times in a row, like until I saw a pattern that I could write in sigma notation, would take for it would be too long. It would take more effort than I want. But yeah, I've been meaning to say I forgot yesterday, but you could do these in the way we learned that whatever 4 lessons ago or whatever. But with that said, look at now we're on this problem. Again, you could do this by getting the Taylor series or the Maclaurin series or whatever. But the idea for this one is easier to use yesterday's trick. Meaning, get rid of all these extra little marks that I made on accident. Get out of here, get out of here. Meaning, okay, yesterday we saw that 1 over 1 minus x is equal to this series. That. Cool. Then, I mean, a big hint is that we just had this big box right here telling us you can take the derivative or the integral of these and get a different function using that idea. Like take the derivative of the series and that will give you the derivative of the function as well. So do you guys see what I'm getting at? Do you see a way to get from this series that I'm overlining to this function that I want? Yeah. And if you don't see that, like look at it now, watch this. Here's us getting the derivative of the blue function that I'm highlighting. Derivative of that of 1 over 1 minus x would be equal to exactly this. You don't see that? I think the easier way to do it, rather than doing well, let's just do the quotient rule, but you could do this using a chain rule. But I think maybe quotient rule is easier to see. So here's us doing the quotient rule. That would be low d high low left alone. Derivative of high is 0 minus high d low. High times derivative of low is -1 over low squared. Boom, there it is. And of course, this orange stuff cancels. -1 times -1 is just 1 over 1 minus x all squared, which is exactly what we wanted. You see what I mean? Okay, very cool, very cool. So what I'm getting at now is that to represent this function in orange, it would be it would be the derivative of this series. Okay. This orange function is the derivative of this blue function. Therefore, the orange function can be represented by the derivative of the blue series. Right. Yeah. So this is another thing that when I first saw it, I was like, this doesn't feel right. This is too simple. But it's totally good. Yeah, the derivative of this series would be the series that each term looks like n times x to the n minus 1. There you go. Nice. Cool. Okay, and if you're like, wait, are you sure you can just take this derivative of a series? Or at least that's what bothered me when I first learned this. Yeah, you can, because if you think of that series written out, that would be the series 1 plus x squared plus x cubed plus x to the 4th plus blah, 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 blah. And so if you take the derivative of this, once you see it written out like this, you're like, oh yeah, you're just taking the derivative of each term. Derivative of 1 is 0. Derivative of x is 1. Derivative of this is 2x. The derivative of this is 3x squared. Derivative of this. So on. So since you're just taking the derivative of each term, like like since it's written out as a polynomial, you're taking the derivative of each term by itself. And if each term looks like this in the original, then each term will look like this in the derivative. I don't know if I'm explaining myself, but hopefully you see the connection. 0 times x to the n minus 1 would be 0. 1 times x to the 1 minus 1 would be 0. So 1 times 1 would be the 1. 2 times x to the 2 minus 1 would be the 2x, and so on. Hopefully you see what I'm saying. All right. Nice. Okay, so we did it. And then it says determine the radius of convergence. So let me get rid of all this extra stuff. Now it looks confusing. Get out of here, get out of here, get out of here. It's going to be select. Okay, but radius of convergence, very easy because we already knew the radius of convergence of the old one. Like the radius of convergence of this series, the original one that we took the derivative of, this one had radius of convergence of 1. Because remember, the only way this converges is if x is less than 1, or the absolute value of x is less than 1, meaning that the radius is 1. Cool. Okay, so then this theorem up here, the box up here says that they both have the same radius of convergence. So this guy has the radius of convergence of 1 as well.
Is there a mathematical way to find that, or no?
I mean, yeah, you could look at this like another. The question was, is there like a mathematical way, if you forget that on the test, that you could find it? Yeah, I mean, you could forget about everything you've done. Just look at this series and find its radius of convergence. Like, oh, this looks like kind of a geometric series, or just do the ratio test on this, which would be n plus 1 times x to the n minus 1 plus 1. So that would end up being it. Anyway, you could do this. Take the limit and then goes to infinity. And find the radius of convergence that way, but you would get r equals. Yeah,
Wouldn't really calculate a portion.
I mean, we didn't use the calculator at all here, so I would say the regular.
It wasn't.
The nice one. No, but you could check your answers like we were doing yesterday with the decimals. In fact, let's do it real quick. Oh, here's fidget spinner real fast. Just love these. But like here's us checking our answer, just because I like doing it. The function was this. Okay, trying to match that with a series. We said it should be the sum from 0 to infinity, but okay, let's get it up to 50. What was it? N times x to the n minus 1. Okay, there you go. The red matches it real good up till it diverges. Like within the interval of convergence, the red matches it exactly up until -1. And yeah, okay. Nice. Okay. Find the power series representation now for natural log, unless there's questions on the last one, sorry. Nice. Nice. Okay, then natural log. This one is pretty wild, but I mean, natural log shows up you guys see natural log all the time. So this is a useful one, especially like I said, if you go to higher math, you might see this series expansion of all sorts of functions, including natural log. So this is a useful one. I see a bunch of you guys looking up there, and that's a good idea, except that poster has the natural log of 1 plus x, so that's a little easier to get than just normal x. But yeah, that's nice. Right. Like, yeah, this one always makes me think really bad. I can never just remember this one. This one, I always have to do it the long way and be like, okay, well, normal natural log, that would mean that the derivative is 1 over x, and so therefore the series for that, and so on and so on. So bear with me as we do this. Like I gotta think my way through this. So watch this. Natural log of x. I don't know a series that has, like, we haven't talked about a series that models natural log of x. But what we have talked about is a bunch of series that look like 1 over 1 minus x or whatever. Okay, so the idea is to know that the derivative of natural log of x, in other words, g prime of x, that they call this g, is 1 over x. Okay, and 1 over x, I can model with this series. So I would want 1 over x, which would be 1 over 1 minus, I always need the 1 over 1 minus if I'm going to do a geometric series, you know what I mean? So what should go in these parentheses to make that just normal x? 1 minus x, because 1 minus 1 is 0 and negative. Yes, nice. So 1 minus x. Okay, very cool. You guys good with this from yesterday? This was okay. Nice. And so therefore the series that would represent 1 over x would be, I just need to put this to the nth power basically. So 1 minus x to the nth power. Very cool. Except that's not the answer to this, because that was g prime. So do you guys know what I'm about to do to this? Or antiderivative. Good job, you guys. Yes. I need the antiderivative of each of these terms. Which, again, this feels wrong, but that just means you take the antiderivative of basically this and put a sigma behind it, and you're good. So let's do that. Antiderivative of 1 minus x to the n dx. Okay, so it's kind of tricky, but remember the n, I'm taking the integral with respect to x, meaning the n is like kind of a fixed number in terms of the antiderivative. So the antiderivative of this, you guys see it right away, or should we do it the long way? Yes, good job, except you just took the derivative. But yes, you can do that in the antiderivative sense, meaning you can just add one to the power and divide by the new power. So this would be equal to 1 minus x to the n plus 1 over n plus 1. Except, like Eden just said, if we were taking the derivative of this, there would be a chain rule because this is negative x. So we'd multiply this by -1. And now since we're taking the antiderivative, we would technically need to do a u substitution. In fact, maybe I should have done the u substitution, and I'll do it in a second so you can see exactly what I'm talking about. But there's technically a u substitution that we skipped here that would have given us an extra negative to divide by. Because of the dx here, the du would have had a negative dx. So what I'm saying is this is not our antiderivative, but now if I divide by a -1 or just make the whole thing negative, now it is our antiderivative.
Because it's negative linear.
Because it's negative linear, exactly. It's like when we had 3's in front of these, and I said the antiderivative would be you've got to divide by that 3. But I'll do the u substitution now after I write the answer to this. So my answer would be from 0 to infinity, negative 1 minus x to the n plus 1 over n plus 1. Oh, and that's it. There's my series. I'll convince you of this with Desmos in a second. And then after these two questions, we'll do those u substitution for this so you can see where I'm getting these numbers. Kian and then on.
Or actually, I guess because it's just asking for radius of convergence, so like the C value or whatever doesn't matter. Like where because I don't know. When you find an integral, usually you want the C value.
You're right. Yeah, you want a plus C out here.
But for radius of convergence, does that not matter? It would just be like added on wherever.
No, you're right. We should think about the C value. Oh, I forgot about this.
We could substitute for the endpoint. If I would be fine to see. That we for them to go from here to here on the C value.
No, I think normally what anytime you want to find the C value, you use something that you know about the function. So what I mean is use something easy about natural log to find the C value. So like for example, I know that g of 1 would be natural log of 1, which would be what? Yeah. And so I would want this plus C value. It's going to end up being 0. I would want that plus C value to account for the fact that if I plug in 1 for x, I need the result to be, yeah. Okay, I just don't know how much to explain or how worth it is to go into it. Because I don't think you get asked about this level of I don't think you take derivatives or integrals. But I gotta look into that. But what I'm saying is if I did plug in 1 into the series that I'm claiming this series will represent this function. If I plug in 1 into this series, I do get the 0 that I need because that would just be this series. And 0 to infinity, negative 1 minus if I plug in the 1 that I'm trying to match over here, it would just be the sum 0 plus 0 plus 0 plus 0 plus 0. It would be that sum 0 plus 0 plus 0 plus 0, which would just equal 0, which is what I wanted. So this plus C would be like 0 plus C needs to equal 0. Meaning that C would be 0. But that's a good point. Yes, sometimes you do have to worry about that C.
But we should put the C in the intervals when we show our work, but we can leave the C out because it's 0.
More like what I'm saying is you should check for the C and you should solve for it and all that.
Okay.
But I do not think they ask you about that on the AP. So not worth super stressing about. But Annika, you had something?
Oh, my question.
Yeah, good job, you guys. I forgot about it when I was making my key, but you guys remembered. Nice, yeah, in fact, up here, you'll see that they do have this extra C value. Nice. All right. Well, here's us checking it, how well our thing fit. And I should show you that, like, the internet will tell you something different, but equivalent from what it would be. So here is natural log of x, trying to match that black function. Here's the series we claim should match it. It would be -1 minus over n plus 1. And there it is. It matches it real good within the radius of, oh, we never talked about the radius of convergence over here, but just like before, this has a radius of convergence of 1. Be good for a mouse. So therefore, this has a radius.
Is it like? Couldn't we just look at the linear function that's in the middle? Because it's 1 minus x. We could say it's just 1 because of the like, say like a root is like right there. They're like kind of like the roots.
Say that again?
Is like the 1 kind of like a root, and so therefore we can say it's just 1 immediately. Because if it was like a 2 there, for I don't know what reason.
Oh, wow. No, but yes. Not the 1. Okay, Jeremy, for the video, Jeremy is asking about, couldn't we have just looked at this and known it was 1 because of that one? And the answer is no, you can't know because of that one that it's R equals 1. But you can know because of the fact that this whole thing, I don't know what to highlight here, this whole thing is a geometric series.
Okay. Yeah.
You know that the inside of that would have to be a radius of 1. So what I was saying, no, but yes, is that if this had been over 2 or something, now the radius is 2 because if you were to solve, basically whatever this is divided by, that is going to be your radius.
Okay.
Yeah, and I'll let you convince yourself of that. I don't want to stray too far from, like, I don't want to give you information after information after information. But yeah, you can kind of just look at this. If it's a geometric series, you kind of just look at the x and be like, what would I be allowed to plug in? But these are little tricks that, like, if you don't remember this in 3 weeks when you're taking your AP test, then just do it the long way where you take the ratio test or whatever. All right. Other questions? All right, Joe. Good job. These were the 2 hardest ones. Then it gets easier after that. Yeah. Because watch this. Here we found that natural log is equal to this series within a specific interval of convergence. Orange equals black right there. Orange is the new black. And down here, they're asking you, now give me a power series for that function. So without doing any work or thinking at all, do you guys see a way to get that function h of x? You know?
You literally just multiply the previous grid times.
Legend. Yeah, that's the kind of thing we were doing yesterday. Just to remind you, here's me going back to yesterday. Look at right here, what I'm circling in blue. I knew the power series for that, what I just circled right here, but that had a 1 and this had an x. So I just took this power series and multiplied it by x to get the function that I want. That's that we've been doing this for a couple days now, where we can just take the series that we know for natural log and infinity. Here's the series we know for natural log, like up here. I'm just going to multiply that by x squared so that I get negative x squared of 1 minus x to the n plus 1 over n plus 1. Take that series, multiply by x squared, and I would get this function. In fact, if you, I like just checking on Desmos because I like seeing them match up. So here's us looking at Desmos. Let's make this now x squared, natural log of whatever. Okay, so let me multiply this by x squared, and it matches it on the same rate. Yeah. Nice, y'all. Luckily, this one, well, I won't say that. I don't want to overflow. All right, cool. Then, like I said, it gets easier from here. These were the two most abstract ones. And actually, I think even yesterday's were a little bit hard. So we got hardest, and then now we're on the where everything's downhill. Because we've already talked about everything that's left. These guys, the next few pages just return to Taylor series, which is exactly what we've been talking about for like the past few lessons. Taylor series are the ones that look like this with the you match the function value, you match the first derivative times x, the second derivative times x squared, third derivative times x cubed, etc. Those are Taylor series, and we talked a lot about these already. So it says determine the Taylor series for e to the x about x equals 0. Okay, we know how to do this. We just say, okay, what is f of 0? That would be e to the 0, which is 1. What is f prime of 0? Well, that would be e to the 0 again, which would be 1. F double prime would be 1, etc. So every derivative of this function is 1, meaning every coefficient of my series will be 1. You're remembering this, but if not, I'll go back and show you. So then my function e to the x will be equal to 1 for the function value, plus I need the derivative to be 1, so 1x to the first over 1 factorial I get, but I'm not going to write all that. Plus 1x squared over 2 factorial. Plus 1 for the third derivative, so 1x cubed over 3 factorial, plus, and so on and so on and so on. So in other words, e to the x is equal to this x to the n over n factorial. And that's one of the elementary ones that you have to know like off the top of your head, or at least be able to figure it out real quick in case they ask you tomorrow on May 12th. That's one of the elementary ones. That's one on the poster. This is one that you have to know. Okay. All right, cool. Questions on this? Okay. It's kind of funny that they said find the Taylor series about x equals 0, because that's what a Maclaurin series is. But that's just a wording thing. No, it's the same thing. It's just Maclaurin is only centered at 0, whereas Taylor series, look at the next one. Oh, this one's also around 0. But the one after that is about f equals -4. So that would be a proper Taylor series, whereas Maclaurin series are the ones that are about 0.
So we just plug in a different number.
Yeah. Yeah, and in fact, watch this. Here's the function or the sum for e to the x. So while you could do this on f of 0 here, f prime of 0 here, f double prime of 0, and so on, find all those numbers and do the same thing we just did. You could also just edit your previous answer, because that answer up here that I'm circling, this answer up there, was e to the x. Now I want e to the negative x. So I can just edit the answer from my previous one. So it's up to you which one you want to do. Do you want to do it this way where you find f zero, f prime zero, f double prime zero, or do you want to use this trick? Watch this. There's e to the normal x. Here's e to the negative x if you replace the f with the negative. Cool. So that's a good answer. Question here.
Wait, if you just plug in all the like zero values. Oh, you get one in the negative one.
Yeah. I was just about to do that. Yeah. So if we did this a long way, f of 0 would be e to the negative 0 would be 1. F prime of 0 would be a chain rule, so it'd be e to the negative 0 times negative 1. So negative e, so it would be negative 1. And then times another negative would make a positive 1, then negative, then positive, then negative, then positive. And so how is this reflected here? Well, this is the same thing as, like, maybe had you done it this way, you would have been like, oh, this has to be an alternated series. But that is exactly what we got. If you would have said it's this, had you done it the long way. But those are the same thing, because the sum that I'm pointing at is the same as this sum. And negative 1 times x all to the n, and the same thing as negative 1 to the n times x to the n. We've talked about that part before as well. All right. Are you guys doing fine? Questions? You guys are getting a ton of information right now. Hopefully, it's good. It's gonna make sense. All right. Find Taylor series for f of x around x equals -4. This one you do have to do it the long way, because I don't know, like, we haven't talked about this specific one centering it around x equals -4. So you do, I think, have to do f of -4, f prime of -4, and see a pattern. So that one, see if you can do it. Here's like 2 minutes.
Oh, wait.
See if you can figure out this just to make sure.
Oh, so you're gonna study?
Show for Ken.
Yeah, because e to the negative x, like you just said, just negative positive. There's no what? No, there is negative positive. Oh, but not.
Oh, it's not. X was 4. Yeah.
Nice.
Alright. I did something wrong. Probably did something. Yeah, because you have to do a trade, right? And then you can bring that down, then this one here.
No, not the 4, not the 4. Because it's going to the negative x, it's not.
Be plugging.
Plug in the 4.
Oh. I get it. I understand, yeah, I understand.
Yeah. That's a couple people that, okay, since I skipped the X derivative, like on the last few, I just went straight to plugging in 0 and 0 and then now 4. A lot of people thought the chain rule applied with the 4. But no, if you do the derivatives with X is plugged in and then plug in the -4, like don't try to do it all at once, you'll see that it's just e to the negative x. First derivative is negative e to the negative x. Second derivative e to the negative x, et cetera, et cetera, et cetera. So what I'm saying is plugging in -4 into these will give you e to the 4, then negative e to the 4, then positive e to the 4, and so on and so on and so on. Meaning don't make the 4 a loop. All right, cool. And then so now you know what the function, the first derivative, the second derivative should be. So your these will be your coefficient of your polynomial, meaning e to the negative x be equal to e to the 4 for the function value. Then I want negative e to the 4 for my first derivative. So negative e to the 4 times x. But remember, it's centered around -4, so times x minus -4 or x plus 4. Remember this?
Yeah.
Okay, to the first over 1. That here's me being very consistent. So most people wouldn't write that. Plus e to the 4 times x plus 4 to the second over 2 factorial minus e to the 4. And so on. And so your final answer, if you wanted to put this in sigma notation, would be like this. 0 to infinity. They all have an e to the 4. Well, and that's the only thing that's. Actually, no, that's right. They all have an e to the 4, but it's also alternating. So do you guys remember how to make it alternating? Yeah. Well, yeah. Oh, sure. You could do that. Or you could do -1 to the n power. That will make it alternate. Positive, negative, positive, negative, positive, negative. Then they all have an x plus 4 to the nth power over n factorial. So that should be your answer. Yeah. Okay. Cool. Oh, and now we have 2 minutes left. But like I said, tomorrow will be pretty quick and easy because it's like more of Taylor's theorem. Or sorry, not tomorrow. Good job. No, I have a meeting tomorrow. No class tomorrow morning. Thursday will be easy. We'll finish this, and maybe we can do like AP question on series and on unit 9. Because you're guaranteed to see both of those big time on the test.
Or you come in on Friday morning, even though you're not.
I thought about it. If you want me to, I could.
Like, hey, is there gonna be a sub or something?
Not in the morning, but for the day, yeah. But yeah, if you want me to, I could come in at 8 a.m. and do easy stuff.
It's fine. I'll just go to the conference.
Oh, maybe I could. Okay, I'll figure something out for Friday so that we don't waste the day.